Good morning, everyone. This is Chen Liu from Clarkson University. I'm very glad to have this opportunity to present our research work on high-frequency performance monitoring via architectural event measurement at the SIG-Prime benchmarking in the data center expanding to the cloud workshop. Nowadays, in modern computing systems, there is a significant demand to improve the performance of the software in terms of either speed or energy efficiency in order to maximize the performance. Obtaining detailed software execution information via performance monitoring counters is a powerful analysis technique. The performance counters provide an effective method to monitor program behaviors, which can be used in various applications such as optimization, malware detection, scheduling techniques, and dynamic power estimation. There are many open source tools that have been developed that provide a high-level API to control and collect the performance counters data, such as Linux Perf, Puppy, and Limit. However, there are certain drawbacks for each of these available tools, such as some of them have low timer granularity, while others have high performance overhead. Some of them may require source code modification, while others require the kernel to be patched in order to use the tool. To address these limitations, in this work, we introduced K-LEB, Kernel Lineage of Event Behavior, which is a performance counter profiling tool that utilizes kernel space collection systems to produce precise, non-intrusive, low overhead, high periodicity performance counter data. By moving the collection mechanism to the kernel, it allows us to reduce performance overhead from the expensive system calls. It also allows us to use a high resolution timer, which we call HR timer, at kernel level, which provides a finer time granularity. This figure shows the architecture of K-LEB. The two main components of K-LEB are the controller process and the kernel module, respectively. The controller process resides in the user space and is used to control the kernel module in kernel space by passing the parameters from user to the kernel module to set up, start, and stop collecting the performance counter data. Kernel module is used to access the PMU to set up and collect the performance counter data, while also tracking the process being monitored using the scheduler in the kernel. PMU, or performance monitoring unit, consists of special hardware registers residing in the processor, which is used to monitor the hardware events. And lastly, monitored process is a process of interest, which is a process being monitored by the kernel module. Here shows the 5 phases of the K-LEB workflow. The first phase is the initialization phase, where the user uses a controller process to set up the kernel module parameter, such as target program, hardware events to be monitored, timer granularity before starting the monitoring. The second phase is after the module has been initialized. When the module detects that the monitored process gets scheduled in by the scheduler and begin running, the module will access a PMU to enable the data collection, while also start the timer to periodically collect the performance counter data and store them in an assigned buffer in kernel memory. During this time, the controller process will also periodically extract the data from the kernel module to free up the kernel memory. The third phase is when the module detects that the process gets scheduled out. The module will stop the timer and disable the PMU to stop collecting the data. The fourth phase is when the monitor process exits or the user issues a command to stop monitoring. The controller process will send a signal to deinitialize the module and extract the last batch of data from the module and free up the memory. The data is then logged to file by the controller process in the last phase. For the process interaction, this figure shows the data collection period of K-LEB, highlighted in blue, in relation to the monitored process, highlighted in red. As we can see, after the module setup, it will only collect the performance counter data when the monitored process is actively running to avoid the interference from other processes. And after the process being terminated, the module will be deinitialized and the data being logged to file. We perform our case studies on two test machines. The first machine we use is an Intel Core i7-920 processor, which is of the Helium microarchitecture family. And for the second machine, we use an Intel Xeon Plantium A259CL processor from Amazon Web Services, which is of Cascade Lake microarchitecture family. We conducted 3 case studies to demonstrate the use cases and effectiveness of our K-LEB module and address some of the limitations from other concurrent available tools. For the first case study, we use K-LEB to collect performance counter samples of LinPack benchmark. LinPack is a benchmark used to evaluate the machine's performance by solving a dense system of linear equations. We set up K-LEB to collect the performance counter data for arithmetic multiplication, load and store hardware events with 10 millisecond time interval. From the graph, we can clearly see the phase behavior of LinPack. We can see the sharp increase in load and store events count during the benchmark parameter setup. For a major part of the program, which is the linear equation solving period, in which we can see sharp increase in arithmetic multiplication and load events. We can see the clear transition from loading data and computation followed by storing phase afterwards. Then the pattern repeats for the number of trial runs of the benchmark, which matches characteristic of the program. We also compare floating point operation per second, flops number across different profiling tools to compare the performance loss from using the tools. K-LEB achieves a very small performance loss of 0.64% when compared with Linux Perf, which has a performance loss of 7.08%. This case study also shows that K-LEB can generate time series data samples with non-intrusiveness where no source code is available, as we directly downloaded the binary executable of LinPack from the Intel MKL benchmark suite. In the second case study, we use K-LEB to collect performance counter data from the running Docker containers. We collect the last level cache misses and the retired instructions and use them to calculate the misses per kilo instructions, MPKI, as a metric of the workload. We then use MPKI to characterize workloads into computation-intensive program when MPKI is lower than 10, and memory-intensive program when MPKI is higher than 10. From the graph, we can see that the interpreter Docker images, such as Ruby, Golang, and Python, have very low MPKI, less than 1 on average. They can be categorized as computation-intensive programs. On the other hand, other Docker images, such as MySQL, Traffic, and Ubuntu, despite having higher MPKI than the interpreter programs, are still categorized as computation-intensive programs due to having an MPKI less than 10. On the contrary, the web server Docker images, such as Apache, Nginx, and Tomcat, have MPKI much higher than 10, and thus categorized as memory-intensive programs. This case study is used to demonstrate that K-LEB can monitor and collect the performance counter data on a running program without interrupting the running workflow, as it does not require to interrupt or restart the workflow to start monitoring and collecting the data. We did another run of this case study on the AWS machine. We found that the number of cache misses can vary for each processor due to the different hardware configuration and the cache structure of the processors. But the programs still follow the same trend in terms of their MPKI from high to low. Or that is, the interpreter programs still maintain a very low MPKI on average, and the web server programs still have very high MPKI on average. In the third case study, we use K-LEB to differentiate the program behavior between benign and malicious cases by deploying the meltdown attack. As we know, meltdown is a cache side channel attack that allows the attacker to read the value from the normally would be inaccessible memory locations. Since the meltdown attack mostly revolves around the cache exploitation, we set up K-LEB to monitor the cache events such as cache references and cache misses to calculate the cache miss to cache reference ratio. For this case study, we run a secret string printing program. For malicious case, we print the string using meltdown attack to extract and print out the string from the memory. But for the benign case, we print the string normally without meltdown attack. Since this program have a very short execution time, less than 10 milliseconds, we use high frequency timer of 100 microseconds to collect the performance counter data during the program execution to detect the period of the attack from the meltdown. In the graph, we can see a very high cache miss to cache reference ratio, almost 1-to-1 during the point of attack. This is due to the flush and reload side channel attack meltdown has to rapidly perform to determine the memory location. Also, even though the number of cache events can be different on different processors, we are still able to detect and identify the period of the attack from both testing machines using cache miss to cache reference ratio. This case study demonstrates the importance of high frequency data collection period of K-LEB. This is very important since for the tool like perf can only provide the timer up to 10 milliseconds and cannot generate multiple data points for this case study and thus cannot identify clearly the period of the attack. We performed the performance overhead study for K-LEB and compare it with other timer-based profiling tools using the same sample rate or comparable number of collected samples for non-timer-based profiling tools. From the table, we can see that K-LEB has a very low overhead of 0.68% at 10 millisecond sample rate in comparison with other profiling tools. And K-LEB still shows to have the lowest performance overhead in other sample rate as well. And K-LEB mitigates the overhead effectively by collecting and keeping the performance counter data in kernel space. This method reduces the expensive overhead from extra system calls other profiling tools have to make in order to collect the performance counter data. This graph shows the normalized execution time of the program from all profiling tools. As we can see, K-LEB consistently has less execution time than other profiling tools, and also has less spread in execution time, which indicates the non-intrusiveness of the tool. This table shows a percentage difference in hardware event count of K-LEB in comparison with other profiling tools. We mainly choose architectural events, such as branch, load, and store for comparison. As these hardware events are more stable and deterministic than microarchitectural events, such as the cache miss rate, branch miss prediction rate. This is due to that the microarchitectural events have dependencies on the context and the state of the hardware. Due to the independent characteristic of the architectural events, their hardware events count are also consistent across different processors we used for the case study. When compared with the similar timer-based tools such as perf-stat, K-LEB shows negligible difference, less than 0.0008% in hardware event count on deterministic events. While perf record uses sampling method, which is a non-precise counting to collect its hardware event count, it still has close approximate hardware event count with less than 0.15% difference on deterministic events when compared to K-LEB. For PAPI, which uses instrumentation method to collect its performance counter data, shows more different in hardware events count to K-LEB than perf tools, but still shows less than 0.24% difference on deterministic events. So in conclusion, in this work, we introduced K-LEB, a kernel module-based approach for performance counter collection that have the following advantages. The first advantage is being non-intrusive to the program being monitored, as it does not require source code modification or having to interrupt the program workload to be monitored. It can provide a high frequency sampling rate up to 100 microseconds, which is 100 times finer granularity than the current available tool. It also has very low overhead when compared to other profiling tools, which would be very beneficial for the online and live analysis applications. With this new approach, it allows users to better measure performance and characteristics of programs. As a result, many other subject areas that benefit from using performance data, such as program analysis, malware detection, and scheduling techniques, could advance as well. So I would like to thank my PhD student, Chuchitab Warlit, my former student, James Braska, and our collaborator, Dr. Lok Yan, for working on the K-LEB project. The K-LEB project can be accessed on GitHub using the link shown on the screen. And my research group page can be accessed at camel.clarkson.edu. So this concludes my presentation, and I'll be happy to answer question that you might have. Thank you very much.